All right, so now that we know a little bit about how trade wind inversions form and a little bit about where they're typically located, namely the subtropical oceans, we want to take a look at their climatology. What do they look like? How does this vary spatially? And this information will ultimately prove crucial to our next lecture, which provides a mathematical framework in terms of a lapse rate tendency equation by which we can quantify the contributions of different physical processes on inversion strength. So let's go ahead and dive in. So again, we're taking a focus here on the eastern North Pacific Ocean, although the results would be similar for any of the eastern subtropical ocean basins during their summer months. We take a look at the eastern North Pacific Ocean, in particular this region from near and just west of Hawaii toward the California coastline, because that's where the most data are available to us. There are longer records of data available here than there are elsewhere. So with that in mind, let's go ahead and dig right in. So we take a look at the typical inversion structure, and we have California here in our map here at right. Vandenberg Air Force Base is the location of this particular sounding here, and it's depicted as a typical sounding at the Southern California coast in the summertime. We have pressure here on the vertical axis. We have skewed isotherms, the lines going from bottom left to upper right. We also have our dry adiabats going from bottom right to upper left here. The temperature trace is given by this black line that traces out through the middle of the diagram here. And the numbers are the height, the left one, going from 153 to 420, 810, all the way up to 4420. And then the right one is the mixing ratio value, from 9.8 grams per kilogram to 9, 4.7, all the way up to 1.3 for our uppermost layer here. And there are three distinct layers of note on this sounding. We have a shallow marine atmospheric boundary layer here. So this is the layer that is most affected by the underlying surface conditions. Along the coast of California, we have a cold ocean current that extends from the north down to the south, and so it's typically relatively cold and relatively cloudy in this region during the summer months. And so we see this depicted here with the surface temperature on the order of about 14 to 15 Celsius, 9.8 joules or grams per kilogram of mixing ratio here near to 1,000 millibars. We then have a deep inversion layer, in this particular case extending from about 960, 965 hectopascals up to about 810, 815 hectopascals, over which the temperature increases from about 12 degrees Celsius to 20 degrees Celsius in that time frame. Mixing ratio decreases from 9 grams per kilogram to 4 grams per kilogram over this particular layer. And then above that, we have the free atmosphere, the free troposphere, which is air which has a history of descent in the descending branch of the subtropical anticyclone here. Ultimately, where this inversion is located within the vertical is a function of a number of different physical processes, not just descent from above, but there are lots of processes from below that ultimately influence the inversion strength and location. And in our next few lectures, we'll take a look at just what those ultimately are. So with this in mind, let's take a broad look at the overall view across the subtropical eastern North Pacific here. And we start with sea level pressure here in this map. All of these images are going to focus on July, and they're typically to the common convention for a given field. So in this case, we have millibars, hectopascals from 1027.5 every 2.5 hectopascals extending away from there. We have our area of high pressure well to the north and northeast of Hawaii, well to the west of Northern California here. The heat low associated with the North American monsoon over the desert southwest. And between the two, we have a pressure gradient from the high to the low, with the isobars oriented more or less north-south, and we would expect the surface winds to closely resemble that. If we take a look at just what those surface winds ultimately are, we have our area of high pressure, which I've annotated here with this H near to the center of the pressure anomaly on the previous slide. And as we'd expect with the effects of surface friction, even over water, the flow not only spirals clockwise, but it also diverges away from the area of high pressure. And we see that flow diverging toward the west coast of North America here. Note how some of that comes toward the coast of North America, and that's all that there is to say about that. But then there's other parts that run parallel to the coast of North America, and then there's a component that spreads outward, away from the coast of North America. So there's two key elements that I want to highlight in that particular region. So that area is where we see the maximized directional divergence or diffluence. So we have low-level winds that are spreading apart from each other or diffusing diffluently near to the west coast of North America. But we also have this large-scale clockwise rotation associated with a subtropical anticyclone. And the ocean currents follow very similar to this, where you have the initially warm ocean current, the Kuroshio current from the western North Pacific, cooling, and then we have a cold current extending along the west coast of North America down toward the south. So not only is this area associated with strong low-level divergence, but it's also associated with strong low-level cooling from the cold ocean that lies beneath, as compared to areas further to the west and especially further to the south. So those two components are going to be critical when it comes to understanding factors that influence the strength as well as the altitude of the inversion. Divergence along the west coast of North America, eastern North Pacific, and the relatively cold waters that reside beneath there. If we move forward to a climatology of just how frequently the inversion occurs, note that this is a little bit of a weird diagram. It's the inversion absence frequency. So we want low numbers here to indicate where the inversion is located very frequently. This whole gray shaded region from the California coast westward and southwestward here denotes areas where there weren't observations in a period of June to September without inversions from the data set used to create this image here. So these are semi-permanent features along the west coast of North America and even extending down into the subtropical eastern North Pacific Ocean here. And in fact, if you see tropical cyclones off the coast of Mexico, when they progress west-northwestward into this region here, they typically dissipate very quickly. It's very stable and very cool in this region, both of which are detrimental for tropical cyclones to form. The inversion frequency becomes a little bit less frequent as you move further to the west toward the center of the subtropical anticyclone, and especially further to the south as you move to progressively warmer waters, especially near to Hawaii. Whereabouts in terms of the altitude of the inversion? We can consider both the bottom of the inversion, known as its base, as well as the top of the inversion, known coincidentally as its top. So if we take a look at the altitude of the base or the bottom of the inversion, each one of these contour lines is 200 meters apart, and I've annotated them in from 400 meters all the way out to 2 kilometers. Consistent with that example that we took a look at very early on in this video, the inversion is found very close to the ground right along the coast of North America, and it becomes found at progressively higher elevations, higher altitudes, as you move toward Hawaii, toward the west and southwest away from there. So the inversion is found closer to the ground where the underlying water is colder and where we have strong low-level divergence or low-level diffluence. And we'll find that that's not necessarily a correlation without causation. That divergence actually helps to maintain the bottom of this inversion very close to the surface, as does the relatively cool ocean temperatures that reside beneath. The opposite is true further to the south and to the west. In terms of the top of the inversion, we get the same type of spatial pattern that we did before. Relatively low values right along the coast of North America that then increase as you move to the west and southwest away from there toward Hawaii. We start out at around 800 meters to a kilometer above the ground here over the ocean, and then spread out to 2 to 2.5 kilometers going to the west and southwest. So we're looking at something that has a thickness of roughly about 400 meters everywhere. So we're looking at a relatively shallow feature. That sounding that we took a look at early on in this lecture was pretty big in terms of the depth of that inversion, but more commonly you're looking at something that's relatively shallow, half a kilometer or less in terms of its depth, found very close to the surface near to North America, and it ascends as you go away from North America toward Hawaii. We can see that on a vertical cross-section through the region from San Francisco here at the far right to Honolulu here at the far left. So we're going from east-northeast to west-southwest along this diagram here. And ultimately, each one of these tick marks here is separated by about 500 kilometers, give or take. We have height in meters along our vertical axis that we have here. So we're going from 0 to 3 kilometers above the surface. And all of the contours are isotherms. 24 Celsius here at the bottom, and far left or far west southwest is our highest value. And we have 8 Celsius here at the top as our lowest value. So here near San Francisco, it's colder near to the surface than it is near Honolulu. And that's both a function of the latitude, but also to that cold ocean current that we see along the west coast of North America. The inversion is found at relatively low elevations here, roughly 500 to 900 meters above ground level near to San Francisco. And note how we go from something that's around 14 Celsius to around 20 Celsius as you go upward through the inversion at San Francisco. So we're looking at a change, an increase in temperature of about 6 degrees Celsius here at San Francisco. If we go out further to the west, here at 34 north and 135 west, we have a surface temperature near 18 Celsius that decreases fairly steadily to 8 Celsius or so by the time it reaches the inversion, and then increases back to about 12 Celsius as you go across the inversion. So roughly a 4 Celsius increase. And then if we go over here to Honolulu, we're just above 24 Celsius here at the surface. And then as you go upward, we cool off to about 12 degrees Celsius near 2 kilometers above ground level, and then only warm slightly, 1 or 2 Celsius across the inversion over the next 300 to 400 meters, and then continue to cool off once again from there. So we see that the inversion thickness, this gray shaded region, is pretty similar across this entire vertical cross-section that we have here. But the change in temperature, how much you warm as you go upward through the inversion, is different. It's largest here near the west coast of North America and becomes progressively smaller as you move toward Honolulu. We see this in terms of the spatial plot of the temperature change across the inversion. So just how much does the air warm as you go upward across the inversion from one location to the next? And we see that consistent with our vertical cross-section on the previous slide, we have 6, 8, 10 degrees Celsius, even a maximum of 12 degrees Celsius here north and west of San Francisco in terms of the warming that we see across the inversion near to the west coast of North America. But then as you go west and southwest from there, that decreases pretty rapidly to about 4 degrees Celsius across the inversion, and then further to about 2 degrees Celsius as you move to the west of Hawaii. So again, the inversion is found closer to the surface, stronger, and the top of it is found closer to the surface, near to the west coast of North America, where you have the strong spreading apart of the winds at low levels and the cold underlying ocean beneath it, all of which are going hand in hand to influence the inversion structure there. Inversions aren't just in terms of temperature, but they're also in terms of moisture, as we took a look at on our previous video. And so we would expect there to be relatively dry air associated with the large-scale subsidence at the top of the inversion. And so these isochrones are every 10% in terms of relative humidity, and we see that it is relatively dry, roughly 30 to 40% above the inversion across the entire region from the west coast of North America west-southwestward toward Hawaii. You get higher values as you get into the tropical Pacific near Mexico and into very high latitudes up toward British Columbia and toward the Gulf of Alaska. But in terms of where we're typically seeing our inversion located, roughly 30 to 40% relative humidity at the top of the inversion. In terms of how much relative humidity decreases across the inversion, note that we're looking at a decrease of 50–60% across much of the eastern portion of the Pacific Ocean near to the coast of North America. So you're going from something that's roughly 30 to 40% relative humidity at the top, and you're decreasing it by 50 to 60% across that inversion, which we can use to infer that the relative humidity is about 80 to 100% beneath the inversion. Whereas as you get further to the west, between Hawaii and the far eastern North Pacific, you're looking at about a 40 to 50% decrease here. So you're going from something that's about 30 to 40% to something that is on the order of 70 to 80% in terms of the relative humidity from above the inversion to below the inversion. So the inversion is associated with significant warming and significant drying as you go from below to above. The amount of warming and the amount of drying are both greatest along the west coast of North America, and the far eastern North Pacific here. Again, coincident with where that strong low-level divergence and strong ocean cooling are located. So putting it all together, the trade wind inversions are strongest and closest to the ground, where that low-level divergence and thus the forcing for large-scale descent, remember our previous video, integrating divergence upward from the surface is associated with forcing for sinking motion, is maximized and ocean temperatures are the coolest, thanks to that southward directed ocean current. Trade wind inversions conversely are weaker and are found at higher elevations where that low-level divergence and thus the forcing for large-scale descent is weaker and where ocean temperatures are warmer, particularly closer to the tropics. So if the descent is not as large, the extent to which you're going to be able to take that temperature and dew point profile from something like this to something that looks like this is not going to be as great, which helps to influence the relative strength of the inversion. So in our next video, and really our next 3 videos, we'll talk about the mathematical framework in terms of a lapse rate tendency equation by which we can actually understand the factors that influence inversion strength and altitude. Until then, thanks for tuning in.